Okay, hey everybody, it's Tuesday night, and I said I was going to do a follow-up on images. So here we go. Here are the PowerPoint slides that I think I whizzed through one, and then I didn't talk about the other ones. And I think I made it this far that there was a circular definition that an image is a 2D array of pixels, and what's a pixel? It says a pixel is a minute area of illumination on a display screen, one of many from which an image is composed. So it says an image has lots of pixels, and a pixel is a small part of an image. But I think we all know what they are. They're these little dots of light. And if you think about a square image, then there may be 1,000 in width and 1,000 in height, and so like a total of a million pixels. The way computers organize colors for pixels, they have three channels. And so it's the red channel, the green channel, and the blue channel. And you'll see this abbreviation of RGB for red, green, and blue. And it's important that they go in this order: red first, green second, blue third. So this is not how I learned it when I was a kid. When I was a kid, I learned the three primary colors were red, yellow, and blue. And then I made many experiments mixing Play-Doh. Red and yellow made orange, and yellow and blue made green, and red and blue made purple. And if you would have given me red, green, and blue, I couldn't have made yellow. I don't believe that's, 5-year-old Hank doesn't believe that's possible. But on a computer, it seems to work just fine. And so you can combine things like red and yellow, green, and actually it will give you yellow. So the amount of each color is scored from, at least for the purpose of this slide, 0 to 1, 1 being the maximum, 0 being none. And the next slide, I'll actually say how computers do it in practice. So if you have the full amount of red light possible being broadcast on a pixel and the full amount of green light and none of the blue light, then you actually get yellow, which I find surprising. If you get the full amount of red and no green and the full amount of blue, that's purple. If you get the no red, the full amount of green, that should say, and the full amount 100% of blue, you get cyan. And if you have the full amount of all three, you get white. And if you have none of all three, then you get black. So white is the presence of all colors, and black is the absence of all colors. And so the point is, any color that a computer can make, it's made up with some proportion of red, green, and blue. So then the next question is, okay, how do you represent this? So, when you're saying from 0 to 100%, well, there's 0%, 1%, 2%, 3%, and so there's what, from 0 to 100, I guess 101 different values, right? Because you have to, the off by one issue is 101 different values. And so if we want to represent it with just, is it 0%, 1%, 2%? Well, then we need to have enough bits to represent 100 different values. But it could be that we want to represent it with fractional percentages. So it could be that it's not just 0% and 1%, but 0%, a tenth of a percent, 2/10 of a percent, 3/10 of a percent, and so on. In which case we'd need like 1,000 bits so we could represent each of the tenths of a percent from 0 to 100%. And of course we could even go beyond that. We could have, a million different values for red and green and blue, and then we need lots of bits to represent, each of those different values. So there's some question of how many bits is enough. And so the way that we've answered that question is and when I say we, I mean the community of people who are involved in graphics, and really, well, I shouldn't say we because it's the people that answers all came before me, but to ask, really, what can the eye distinguish? And so your eye can distinguish about 10 million colors, and if you use a mere 8 bits per color channel, 8 bits for red, 8 bits for green, 8 bits for blue, meaning that it can represent values. 8 bits would be an unsigned character. That's 1 byte. 8 bits is 1 byte. And so you can have values from 0 to 255. If you have 8 bits per color channel, red, green, blue, and you have 3 colors, red, green, and blue, then you've got 24 total bits, and 2 to the 24th is about 16 million colors. And so it turns out that by using a mere 8 bits, you can get to 16 million colors. And our eyes can only distinguish about 10 million colors. So if we used more bits, well, we'd just be creating colors that we probably couldn't distinguish. And and so we really stopped at 8 bits. And 8 bits, 1 byte, is a very magical thing for efficiency. So it's all good. Now, it turns out, I think this is interesting, there's actually colors we can distinguish between that the computer can't make. And of course, there's many colors the computer can make that we can't really see. Obviously, it can make 6 million colors that we can't distinguish between. Or at least we can see one color, and then there's a pair that it can generate with it, and we can't tell the difference between the two. 6 million times. And so anyway, but I think it's interesting that actually some of the 10 million we can distinguish are things that the computer can't do. So the point of this discussion is that when we represent colors for a pixel, we're going to do it with 8 bits. We're going to organize it into red, green, and blue. And then if it's full red, the 100%, 0%, 0%, we would actually write that as 25500, meaning everything, red being full color, green being no color, blue being no color. And then if we want something that's pure green, well, then it'd be red has no color, green has the maximum, and blue has no color. And full blue would be 0, 255, 0, 0, 255. And so there's different ways to arrange images. So an image is going to be a 2-dimensional array of pixels. And so one way to do it is actually to make, I guess, a 3-dimensional array. If there's m pixels in width and n pixels in height, then there's 3 bytes in depth for RG and NB. And so this is a pretty common way to store data. And let me just start coding, and we can look at it. So I'm actually just going to get inside project 1A. And so in this project, there is, again, we're using the VTK library, and there's some includes that bring in various header files in VTK. And there's a function that I've written for you that creates a new image, and you give it a width argument and a height argument. And then there's also a routine that does I/O. So this returns an image, return value is an image, and then you can pass this image argument into the write image function and a file name, and then it will do its VTK magic to write out a PNG file. And that's nice because it takes a little bit of work to write out PNG. It's not a really simple format, and so it's hiding all those details from us. So what we're doing here is we've made a new image that's 1024 by 1024. I don't like that I've got the same number there. I'm actually just going to make this be 512 by 1024 because I just want it to be a different number in width and in height. And so how many pixels do we have here? Well, we've got the width. We've got the width is 512. And we've got the height is 1024, and so that means that the width times the height is, about 500,000. Here, let's get it exactly right. So that means we've got 524,000 pixels, but each pixel has 3 bytes. 3 unsigned cars, because an unsigned car represents 1 byte, and we want to have 8 bits, and 8 bits is a byte, so the 8 bits is an unsigned car. And so that means the number of bytes that we would allocate here would be 524,288 times 3, which is about 1.5 megabytes. So that's how many bytes we're allocating. And then the question is, well, how do we set these bytes? So it turns out that they're organized, and that's the purpose of this slide, that they're stored as, because it could be stored as, let's have the the red value for the first pixel, the red value for the next pixel, the red value for the third pixel until we get the final red value, and then the green for the first pixel, the green for the second pixel, and so on. That would be one convention, and that would be fine. It's not the convention that's often used, but it would be a fine convention. The convention that's used more often is that you have, for the first pixel, all three of its channels, red, green, blue. Red always first, green always second, blue always third. And then for the next pixel, red, green, blue, and so on. And that the first pixel is at the bottom and left of the image. People don't seem to like that. They want it to be at the top. It's at the bottom. And then this would be, if the width is m, then pixel p of m minus 1 is the bottom right pixel, and this monstrosity is the top left pixel. I don't think that's right. I think this should be p of m times n minus 1 is the top right pixel. So let's try to do this. Oh, so just doing some ASCII art. If we had an image that was 4 by 3, then what we're saying is we'd get P0, P1, P2, P3, oops, P4, P5, P6, P7, P8, P9, P10, P11. And, you know, I'm just going to switch this to hex because I don't want to, it bothers me that they're not all lining up. So now this is in hex. A is 10 and B is 11. And so this would be the layout. And then actually if you allocated a buffer, there would be 36 bytes. And the first byte would be P0 red, and the next byte would be P0 green, and the next byte would be P0 blue, and then P red 1, P1 red, and so on until we get all of the 36 values. And so this would be how it would be laid out in a array of an image that's 4 pixels in width, 3 in height. That's 12 total pixels. 3 color channels would have 36 values, and they'd be laid out this way. So let me just comment that out. And let's have fun modifying our VTK image. And so here we're allocating our 1.5 megabytes, and then when we call this function right here, it's actually getting us a pointer to the very first byte of the 1.5 megabytes. So we would be within our rights to access buffer 0, and we'd be within our rights to access buffer of 1,572,863. That's fine. But we wouldn't want to go here. We'd be actually going past the end of the buffer. So I'm just going to turn the first, let's say 10,000 pixels red. So I'm going to say for int I equals 0, I less than 10,000, and then so what I'd like to figure out where is buffer, where is pixel I. And so you can see here as we look at this example, the pixel 0 is at index 0, pixel 1 starts at index 3, pixel 2 at index 6, and so on. And because each pixel has 3 unsigned characters. And so we can do this, we can say index equals 3 times I, and then we're going to set buffer of index for the R channel to be 255, and then for the green channel to be 0, and the blue channel to be 0. So we're going to overwrite the first 10,000 pixels. We find the offset in the array, and then we set the red channel, which is the first one, to be at 255, green at 0, and blue at 0. So looking at this up here, if we're doing that to this example, note that I wanted to get everything lined up because I'm just that sort of programmer that I wanted everything to make a straight line going down. This would mean that we'd want to set index 0 to 255, index 1 to 0, index 2 to 0, index 3 to 255, 4 to 0, 5 to 0, 6 to 255, 7 to 0, and 8 to 0. And if this was only happening over the first 3 pixels, then the first time through, this would be 3 times 0, which is 0. We'd set 0 to 0, I'm sorry, 0 to 255, 1 to 0, and 2 to 0. That's good. The next time through, we'd set I equals 1. This would be set to 3, and then we'd set 3 to 255, 4 to 0, and 5 to 0, and the next time 6 would be 255, 7 would be 0, and 8 would be 0. So I think we're good here. Let's compile it. Uh-oh. Oh, good, no problem. So the problem is that we've got nested C-style comments. I'll just address it this way. Now we'll just make a global variable. Should we be doing global variables? Probably not, but it's the easiest way to solve our compile problem. And then I'm going to run my program. And if I look at the output, then the first 10,000, we have about 500,000 pixels, so the first 10,000 is only like a 50th of them, and they're all being set to red. So another thing that I just want to focus on really quick is how to do indexing. And so there's a formula, and you know, I get really confused when I try to say this in terms of x and y or I and j. I like my variables to be int r for the row and int c for the column. And so, like for example, P6 is at row 1, column 2. And I'm actually counting from the bottom. So I'd say PA is at row 2, column 2 again. And so there's a formula, and the formula is that the index for a given row and column is the row times the width of the image plus the column. And so in this case, 6 is equal to 1 times 4 plus 2. So this is the row 1, this is the column 2, 1, 2, and the width is 4 pixels. And A, which is 10, is equal to 2 times 4 plus 2. So when you're in a world where you want to be setting pixels at a given row and column, you would do it with this formula right here. So I'm going to go back, and I'm going to say, so we've got 512 in width and 1024 in height, and I'm going to do the wrong thing first, and I'm going to try to set the diagonal to be yellow. Now, of course, the diagonal stops when we get to a width of 512 and a height of 512. I'm trying to set based on the height, and what that means is I'm going to go outside the bounds of the image, and we'll see what happens. Probably bad things. So this one was setting 10,000 pixels. This is only setting 1,000 pixels, but I'm going to set my index is equal to, well, so in this case, I'm going to set because it's the diagonal, I'm going to set the row equal to j, and I'm going to set the column equal to j too. Now, do I need these variables? I don't. I just think it's clearer to write them. The index is equal to row times the width, and the width is 512 plus the column. And then I'll just copy this code, and if I want it to be yellow, then I'd say red is full, green is full, and that would give me yellow. So if I compile this, and then I refresh the image, not good. I'm actually surprised how this went wrong. I think I've made another error. Let me look at my other error. I think I forgot to multiply things by 3. So you see here I took the index 3 times I, and here I had to do it 3 times I again. So this formula gives me the formula of the pixel, number, P0, P1, P2, etc. But since there's 3 unsigned characters per pixel, if you actually want to find the offset into the buffer, you have to multiply that by 3. So let's do it again. Aha, and I got a segmentation fault. And that's not super surprising because I've written outside the buffer. At some point, I created an index that is bigger than 100 and or 1.5 million, and then when I tried to write to it, it crashed. And so this is definitely something to look out for, that you don't want to be writing to pixels that are, less than 0 or bigger than, in this case, 1,572,863. Of course, the image sizes will change. So I'm going to do this again, and I'm going to now stop when we get to a width of 512. And then as I run it, I've now gotten the yellow diagonal. So that's what this all says right here. And we already talked about the channels. And there's 3 channels, red, green, and blue. As we get further in the course, we'll actually start talking about a transparency channel, the alpha channel. And so sometimes there's the alpha channel is stored. If you've ever done PowerPoint and you get images where there's like a logo and you put it on and it's already clear where the logo doesn't exist, that's because it's using the alpha channel, and you can actually store that in your images. So that's it for my PowerPoint, and hopefully this was helpful for explaining pixels and images and how to manipulate them, and just for getting going on Project 1A. Good luck, everybody.